Hello there. In this video we're going to work through a few examples that illustrate how to find the value of particular definite or improper integrals using the gamma function and the Euler-Mascheroni constant. So let's look at the first example. Let's consider the integral from 1 to infinity of the natural log of x divided by x squared dx. If you want to try out how to do this integral on your own, you can suggest stopping the video and trying it on your own and see if you can get the same answer as I. So how we're going to begin is we're going to begin by getting rid of this interior natural logarithm, which we can do by letting x be equal to e to the u. We have an x squared term, so finding out what x squared is going to be useful later on down the road when we start doing our substitution. So also, if x is equal to e to the u, we can find the differential of x is going to be eu times the differential of u. Let's work out our limits for x. So x is going to go from 1 to infinity. So when 1 is equal to e to the u, the only value of u that's going to make this true is going to be 0. So when 1 is equal to, or when x is equal to positive infinity, the value that makes this true is going to be positive infinity as well. So those are going to be our limits of integration. So our integral is then transformed into the integral from 0 to positive infinity of the natural log of e to the u divided by x squared, which is e to the 2u, times dx, which is going to be equal to e to the u du. So this interior expression just cancels and leaves us with u. So we're just left with the integral from 0 to infinity of the natural log of u divided by e to the 2u times e to the u du. So we have two exponentials on bottom and one exponential on top. So that's going to cancel with two of those. So now we're just going to be left with the integral from 0 to infinity of the natural log of u divided by e to the u du, which we can write in a more familiar fashion, namely the integral from 0 to infinity of e to the minus u times the natural log of u du, which we know is the negative of the Euler-Mascheroni constant. So that would be the answer. Let's do another example. Let's do the integral from 0 to infinity of x to the fourth times e to the minus x cubed dx. So I'm going to begin with a substitution because that's probably where a lot of people will start. So I'm going to let u be equal to x cubed. So du is going to be equal to 3x squared dx. So dx is going to be equal to du divided by 3x squared. It's very easy to see that the interval for x, 0 to infinity, is going to be mapped to the interval 0 to infinity for u as well. So this integral is then transformed into the following. So we have the integral from 0 to infinity of x to the fourth times e to the minus u times du divided by 3x squared. So we have 2x squareds, or x squared there, and we can cancel that to make 2. So we just get the integral from 0 to infinity of x squared times e to the minus u du. So how can we replace this expression with that expression? So if u is equal to x cubed, then x is going to be the same as u to the 1/3. So I'm going to replace that in this place of x. So this is going to be equal to the integral from 0 to infinity of u to the 2/3 times e to the minus u du. Alright, so let's also not forget about this 1/3 that's hanging out. So let's bring him out. So 1/3, 1/3. So this is the same as 1/3 times the integral from 0 to infinity. So this is going to be the same as u to the 5/3 minus 1 times e to the minus u du. So the reason I'm expressing it this way because this integral is related to the integral from 0 to infinity of t to the x minus 1 times e to the minus t dt. In this case, t is the same as u, and x in this case is 5/3. So this, as we know, is the gamma function of x, which means this expression is the same as gamma of 5/3. So therefore, our integral is going to be equal to 1/3 times gamma of 5/3. So that is the value of the integral we have. Alright, so let's work on another example. So example 3. Let's consider the integral from 0 to 1 of the natural log of the natural log of 1 divided by x dx. So I'm going to begin working on this interior function, so I'm going to be letting, let's let u be equal to 1 over x. So we can let du be equal to negative 1 over x squared dx. So that means dx is going to be equal to negative x squared du. For our integrals, this is a right-handed zero integral because we're going from 0 to 1, not say negative 1 to 0, which would then be a left-hand 0. So we have 0 plus to 1, so let's figure out some limits here. So when x is equal to some number from the 0, what do we have here? So u is going to be equal to 1 divided by 0 plus. So we know this is going to go to positive infinity if we approach 0 from the right-hand side. So if x is equal to 1, then u is going to be equal to 1 divided by 1, which is going to be 1. So our integral from 0 to 1 is going to go to the integral from infinity to 1. So this is going to go from infinity to 1 of the natural log of u times dx, which is going to be negative x squared du. So we're going to take this negative and we're going to flip our integral into a more comfortable representation. So this is going to be equal to the integral from 1 to infinity of the natural log of u times x squared du. So what can we do with this x squared term here? So let's see. So we know that u is equal to 1 over x, so we can say that u squared is going to be 1 over x squared, which means that x squared is the same as 1 over u squared. So we're going to replace that into this expression. So we can rewrite this entirely in terms of u, so the integral from 1 to infinity of the natural log of u times 1 over u squared du. Alright, cool. So from here I'm going to do a u substitution again. Now I'm going to let u be equal to e to the x, I believe is the best substitution. So du is going to be equal to e to the x dx. So dx is going to be equal to du over e to the u, or du over e to the x. U squared is going to be equal to e to the 2x as well, so we'll use these two facts. Also, our integral bounds, so 1 to infinity for u is going to go to something for x. So when u is equal to 1, x is going to be equal to 0, and when u is equal to infinity, x is going to be equal to infinity as well. So our integral turns into the integral from 0 to infinity of the natural log of u, which is e to the x, times 1 over u squared, so it's going to be 1 over e to the 2x. Du is going to be equal to e to the x. And what do we have? So this integral should begin to look familiar. So it's going to be equal to the natural log of x times e to the minus x dx, which again we know is going to be equal to the negative Euler-Mascheroni constant. So let's work out another example. So now we're going to let a and b be, say, natural numbers. And we're going to consider the integral from 0 to infinity of x to the a times e to the minus x to the b. So we're going to do a more generalized example of one we did earlier. So we're going to begin the same way. We're going to focus on this x to the b constant. So let u be equal to x to the b. So du is going to be equal to b times x to the b minus 1 dx. So dx is going to be equal to du divided by b times x to the b minus 1. Alright, so b is a positive natural number by assumption. So when x is equal to 0, u is equal to 0, and when x is equal to infinity, u is going to be equal to infinity. So our limits in terms of x is going to go to 0 to infinity in terms of u. So nothing crazy happens there. So we have the integral from 0 to infinity of x to the a times e to the minus u times dx. So that's going to be du divided by b times x to the b minus 1. So again, u is going to be x to the b, so that means x is going to be equal to u to the 1 over b. So I'm going to replace that in terms of x here. So this is going to be equal to the integral from 0 to infinity of u to the a over b times e to the minus u times du over b times x to the b minus 1. Maybe I could have left this here so I can deal with this this division of x terms, and I'll replace it later. So this is going to be equal to the integral from 0 to infinity of x to the a minus b plus 1 times e to the minus u du. So now I'm going to replace x with u to the 1 over b into this expression. So I didn't have to do multiple x's here. So we have the integral from 0 to infinity of u to the 1 over b raised to the power a minus b plus 1 times e to the minus u du. So we're pretty much building a gamma function-like expression here. So this is going to be equal to the integral from 0 to infinity. So we're going to divide everything by b. So we have u to the a, let's do plus 1 minus b all over b all over b, e to the minus u du, which is the same as the integral from 0 to infinity of u to the a plus 1 over b minus 1, e to minus u du. So this should look familiar. The integral from 0 to infinity of t to the x minus 1 times e to the minus t dt. So I'm going to be focusing on x to be a plus 1 over b. So therefore our integral is going to be equal to what? And I believe we forgot our little constant again. Ah, there he is. There's our 1 over b. So let's bring him out. Yeah, constants seem to slip away often, but we found him. So we have, it's going to be equal to 1 over b times gamma of a plus 1 over b. And these are just some integrals that you can solve via gamma and the Euler-Mascheroni constant, but there are definitely a lot more than you can solve. But this gives us some demonstrations on how you can actually approach some of these integrals with these things in mind.